Welcome to part two for the basics of vectors. Hopefully if you've watched the first one, I probably should have put this disclaimer up, and I might say this every single time. I am very informal, and I will probably say something that is wrong. So if I do, let me know if you're somebody that that's really important about, and I'll go through and I can try to correct it. But I was always got in trouble teaching and not always being perfect. But I found that, especially in teaching mathematics, it's the imperfect, I think, where we learn the most. So what I want to kind of work through in this video specifically is vector representations and get into vector operations. And then in our final video, I would like to try and keep it into 3 parts. I will then get into vector operations graphically, so visually speaking what happens, and then the algebra will kind of make its appearance again. But I feel like those examples will take, I mean, not super long, but enough to where I want to make sure that you have a break and kind of partition it up some. So again, here I really want to hit on vector representations. How do we write? How can you see them? How might you have seen them already? AKA in the first video, when we've talked about a vector v, we can describe it in terms of its components. We can say vx to vy. I can use parentheses, say this v1, v2. And something that I even want to kind of mention here, because typically when it comes to an Algebra 2, a pre-cal, when you start to learn about polar coordinates and vectors for that, you start using the letters A and B to represent the components. And so I'll kind of bring that in here. But again, this representation, whenever we want to write a vector in this form, this is referencing its component form. Component, again, just implying the pieces that make up the entire vector and help determine how we can sketch it and look at it, which I'll do more in a minute. Now, another form, way to represent a vector, and I'll represent the same vector here, is what's referred to as its unit vector notation. And again, if you have taken multivariable, I do not believe you see this in a second semester calculus class, but you may, just depending on the course structure and the way that it's designed. When I reference a unit vector, I'm talking about a vector that is only 1 unit in length, not referencing its actual measurement, so in terms of it being a mile, an astronomical unit, or something like a millimeter. We're just referencing a vector that is literally 1 unit. And so if I go to a graph and I go to a coordinate system, whenever I'm looking at a vector, we have 2, at least in R2, we have 2 elementary unit vectors. The first one is referenced as I, and that is the unit vector that works in the horizontal direction. So this is the unit vector I. I could describe I in its component form as being 1, 0. It's only 1 unit in length, and because I'm only going horizontally, that means I have to only travel in terms of 1 spot. And then I have the vertical unit vector J, which I can describe as 0, 1. And these are called the unit vectors, the primary unit vectors. And how they come into being and where their usefulness comes in terms of notation for vectors is, again, if we reference the V that I had drawn earlier, which I'm going to see if I can remember, I believe it was 4, 3. If I draw that again at this point here, so this was 4, 3 was my terminal point, this is my vector for V. Remember that, or recall that, especially if you saw the first video, that we could look at this horizontal component here, this vertical component here. Well, that's just being made up of multiples of i's and multiples of j's. Excuse me. Where notice, if I'm trying to get to 4, that's going to require me to take 4 I steps. And then it's going to require me to then take 3 j steps to go up. And so just notice in terms of, at least in English as you say it, I'm going to be traveling 4i and then 3j. Well, the word and, specifically in terms of operations, maybe not so much in terms of logic, but in terms of algebra, is addition. And what we'll learn about, or at least discuss in the following video, is that when I'm adding vectors together, 4i plus 3j, we are creating this final resultant vector here, which is my vector v. So we've kind of come up with another way to describe these components as multiples of i's and multiples of j's, or unit vectors, thus the unit vector notation. So for my example here, I could have v is equal to 4i plus 3j. And this is what's referred to or referenced as unit vector notation. And this can be applied to a three-dimensional vector. We just kind of follow the unit vector notation. So if you recall the z-axis, we've got our I, we've got our j, and then my z-axis we refer to as k. That would be the unit vector in that spot. So that means any point that is in R3, that three-dimensional space, could be described, at least from the origin, as unit vectors of I, j, k. And so again, in R3, I could write out v as something like 4i plus 3j plus, and I don't remember if I gave it a number, but let's just say 6k. And that would result in a vector in 3 dimensions. And one of the things with unit vectors is we won't really see this notation very much when it comes to linear algebra, because once we extend past 3 dimensions, we kind of start running out of these unit vectors. Visibly speaking, we're breaking out of the normal Cartesian system. And so at least for what we're going to get into the Unit 1 and Unit 2 and Unit 3 and so on and so forth, we're not going to really be using these unit vector notations. But again, depending on the math courses that you have taken leading up to this point, you may or may not have seen these. And so I just wanted to bring this notation back to you. If you're preparing for a multivariable, or if you just came from a multivariable, these should be very familiar. And as you have worked with these, doing dot products and cross products, we are going to do the same thing, but using the component form, which I think you will find hopefully is a little bit simpler, because we get to strip away all of the extra unit vectors and that notation. And again, depending on who you are, that could be offensive, because you may love these notations, but in our world, I deeply apologize. We probably will not be using this notation very often. The last way that we can describe, last primary, and I'm going to show you one extra one that I thought was, I think, important to show, because you'll kind of see myself use this notation a couple times. And in my studies, and in my master's, is the notation that I used a lot. So there's really, I guess, 2 more. But another way that we can describe a vector, and this is what this one is mostly used in terms of physics and natural sciences, is using the magnitude and direction to describe a vector and represent a vector. Since vectors are mainly constructed using both of these pieces and defined as these pieces, again, specifically in physics and describing motion and forces, if I just give magnitude and direction, we can then sketch out a vector. This is telling me where it's pointed, and this tells me how far to draw the line, and that's at its core all an arrow, all a vector really is. So when I look at this in terms of notation, we need to be aware of it. If I'm trying to describe the vector v, when I want to talk about the magnitude or length of a vector, in linear algebra, we will use the double bar notation for this. And this is referred to as a norm. You may have heard of this language, you may have not. You might have seen in algebra the use of single bars. This is the absolute value symbol, representing distance from 0. Notice a very similar conversation here, that if I'm talking about magnitude, we're talking about the distance between 2 points. For a vector, again, we will use 2 bars, and that's what kind of distinguishes it from a one-dimensional number line distance from 0 to a vector, which we're now still measuring to the origin, but in terms of different dimensions, allows us a little bit more flexibility. Now, the notation that we'll use for the direction, very classical, is our theta. And so when I want to describe a vector, we can describe the vector using its magnitude and direction. Now, again, if you are, and you should have taken pre-cal, if you have gotten into, I believe, Cal 2, a second semester class, you should be familiar with polar coordinates and the polar coordinate system. If you think about how that system is notated, it's notated as r comma theta. Well, r is that distance from the origin, that's my magnitude, theta representing the direction for my point, vectors and polar coordinates are very, very, very connected, which means we can bring in trig, sine, cosine, tangent, all of that to help describe the components, which is why you see trigonometry used so much when it comes to help illustrate 1D kinematics, 2D kinematics, forces, etc. So we have magnitude and direction as kind of our third way to represent. Our fourth and final way that we can represent a vector is what I refer to as the array model. And this is the model that I think is going to be a little bit more relative to us. I think it opens the door more in general for outside of physics and natural sciences courses, so computer programming, etc. Because the array is more about the ordered list than it is the actual components of the vector themselves in terms of like right motion, vertical motion. We want to think about it in terms of, again, if I want to think of V as V1, V2, V3, V4, the array model will place this like so, V1, V2, V3, V4. And theoretically, we can list them in a vertical column, or I can list them in terms of a row. So vectors can be illustrated or oriented certain ways, and then as we work with them, will become very important in what helps create what we refer to as matrices, and the columns of a matrix and the rows of a matrix. And now we can help illustrate them and start thinking about them as vectors, which is going to be really, really important. But we will get to matrices and help review matrices in the next set of videos. And that will be a much shorter because our first chapter is primarily about matrices and working with them. And so this array representation is something you're going to see me use a lot. The component form is what you're going to see me use a lot. Not so much the magnitude and direction. Now we will be concerned with lengths of vectors and talking about their magnitudes. Same thing with direction, that'll come up. But again, primarily arrays, components, not really dealing with unit vector notation that much. So last thing I want to hit on in this video before it drags on too much and I put everybody to sleep with my lovely voice, is vector operations. So now that we kind of know how to represent and how to write a vector, we semi-know how to sketch one. We'll discuss more visually in the next video. Want to kind of know, all right, what can we do with vectors? It's a very similar argument to when we're discussing numbers. Kind of came up with these man-made representations for counting, and then wanted to sit there and say, okay, well, how do we add? How do we subtract? How do we divide? How do we multiply? What are these binary operations? And what do they mean? Excuse me. And so when it comes to vectors, we want to ask the same question. What can I do with vectors? What operations are allowed? Can we multiply vectors? Can we divide? Can we add? Can we subtract? Etc. And so what I want to go ahead and define for you are the primary vector operations that we have. So these are the things that we are allowed to do. It turns out that you cannot divide vectors. It's not an operation that we have. We can multiply with vectors, we can scalar multiply, we can add, we can subtract. But what we cannot do is necessarily divide, and we'll get more into that later on. And so to help illustrate that, let's consider that we have two vectors. I have a vector u, which will give the components as u, x, uy. We'll kind of refer to this notation, it's what I use in my notes. V will be my second vector, which I'll call Vx and then Vy. And one of the first operations that we'll look at very quickly is addition. So what happens when I want to add two vectors together, u plus v? And again, we'll kind of primarily focus on the algebra here and then dig into graphically what's going on. And that'll shed some light on why the algebra makes sense. But the algebra is very, very intuitive, which is why I'd like to go ahead and show you this now. That if I want to add two vectors, it makes sense that we're going to add like components. So that u plus v is constructed by ux plus vx, comma, uy plus vy. In other words, we add like components. And part of this you can see physically speaking, if you were to throw something in the air and then add an extra force to it, its motion is dependent on only the horizontal pieces adding together and then only the vertical pieces adding together. And there's many experiments that kind of look at that and that you could play with in terms of forces and arrows and how things move. But again, when we work with vectors, we add like components. When we want to scale a vector, I just got done teaching geometry in the fall semester of 2025. Scaling, dilating, whenever I want to change the size of something, but I don't really want to change its shape. I don't really want to change its direction, although we can. We'll talk more about that visually in a little bit. If I just want to change its magnitude, right, its length, we do that by multiplying our vector, and I'm going to use a Greek symbol for this, lowercase alpha. We can multiply a vector by some kind of scalar. So when I do this, the vector that gets created, which I'm just going to kind of write as a ux uy here, this multiplication. I hate to say this, but it feels like distributive rule. It is distributive rule. When I multiply a vector by a scalar, each individual component is getting multiplied by that scalar. And again, I will kind of prove this for you visually with an example in the next video. But it's how we work with and multiply vectors. You can view this as distributing, but at its core, it's not really distributive property. We're not adding, and it's not the pure algebra there. But now this is true for alpha is a real number. And so I want to kind of give you this notation now where, again, kind of hopefully a poor alpha there. This kind of looks like a backwards letter E. It's the word epsilon. And it stands for element of. And again, if you ever have the chance to take a discrete course, I would highly encourage it, a logic course. You kind of learn about all of this before getting into advanced mathematics courses. It just means that alpha is an element of, it's in the list of the set of real numbers. So we can multiply a vector by any real number. And when I do that, we're just going to multiply its like components. It's getting stretched. If I want to double a vector, we need to double its horizontal component. We need to double its vertical component. Because we want to maintain the direction. I just want to change its length. And again, we'll kind of see that a little bit later. So hopefully that kind of makes sense. Now, the other type of operation that I want to show you, so I'm going to erase these two now. We're going to talk more about subtraction later, is what is referred to as dot product. Now, when we talk about dot product, we're looking at a specific operation. I actually need to leave this up here. That I'm not going to formally define its purpose yet, because part of the goals and objectives of linear algebra is to better define what this operation means. And again, if you've taken a multivariable calculus class, you should be familiar with the word dot product. And you may have performed this operation before, so you might be used to this and might know the answer. But for now, I'm not going to get into it because, again, we'll do this in terms of chapter 1. And so what I'm doing is I'm not multiplying the two vectors together. What I'm doing is I'm doing their dot product. And I know product means multiplication, but it's very, very, very specific. Because the answer to this is not a vector. The answer to the dot product is a number. And what this number will tell us is some really important information about our two vectors. And again, we'll get more into that later on. And the way that the dot product is defined is instead of addition where we add like components, when I perform dot product, we're going to multiply like components and sum up all of those products. So in this kind of example where I have two vectors that are in dimension 2, so R2, I'm going to multiply both of my x components plus multiply my y components. So it looks something like this, ux vx plus uy vy. And this would perform the dot product. If we had more components, we would multiply those components and add all the way down the line. Now, what you can kind of see from this, and we'll talk more about this later, is that the dimensions of these vectors to perform the dot product, they have to be the same. We can't perform dot products with things that aren't the same. And so we have to be in the same dimension in order to compare and perform this operation. And so this is what's referred to as the dot product. Again, something not to worry about now, but I just want you to be familiar with before we start really digging into the material. The last thing that I want to show in terms of vector operations at this point is the length of a vector. This should be very familiar especially when working in 2 dimensions, is that if I want to measure the magnitude of, let's say, the vector u, and in my notes I think I did u, so this is perfect. The way that I find the length here, the length of that arrow, and if you think back to when I drew this picture, the answer should become quite evident. It's all trigonometry. If I want to know what is the length of this vector, the distance here, I am asking what is the length of that hypotenuse. Well, to find that length, if I know the horizontal component and I know the vertical component, we can find it using Pythagorean. Well, in terms of our component form, I know that this is ux and this is uy, so therefore this is the square root of the x component squared plus the y component squared. And that'll calculate the length or the magnitude of my vector. Now, after just talking about dot product, one thing that might go unnoticed is what I want you to kind of see here is that the length of this vector can also be represented as the dot product. This is the dot product of u dot u. And we're going to talk more about this, and you're going to see this a lot later on. So again, just kind of noticing how this dot product arises, specifically connected with that length of the vector. All right, so that kind of runs us through the operations. There is one more called cross product that you may be familiar with. I'm going to save that, and we'll talk about that one later on. But for now, there's our algebraic operations. And the next part, and I may do a part 4, we'll kind of see how part 3 goes. We will get into graphically how are these represented, what are these actually doing visibly to fully make that connection, and then a small discussion at the end there to kind of help follow that.